Welcome to webinar AMR 101 hosted by KELO Robotics and Hokuyo. In this session, you will learn to build an autonomous mobile robot from scratch. This webinar is made up of two main sections. The theory part, where you learn about the basics and the AMR architecture, and the practical part, where you will become familiar with Robile, our platform, the integration with Hokuyo LiDARs, and the demo robot. Here are our great speakers from Hokuyo and KELO Robotics. We will have a brief round of introduction, and we will start with Hokuyo experts, Dr. Christou, Mr. Yamazoe, and then we will go to KELO experts, Leonardo Tan and Armin Shahsavari. After that, Armin can kick off the session. Okay, so please, Dr. Christou.
Yeah. Hello, everyone, and thank you for joining today. Yeah, my name is Meres Christou. I am the branch manager at Hokuyo Amsterdam Branch. I lead business development across the EMEA region and also contributes to the R&D and international standards as part of the IEC committee. I'm also a TÜV certified functional safety engineer, and I work closely with our customers to implement reliable, standard compliant LiDARs and sensor solutions for industrial automation, robotics, and beyond. I'm looking forward to sharing some insights and practical experience with you today. Thanks.
Hello everyone, my name is Kosuke Yamazoe. Thank you for joining the webinar today. I joined Hokuyo in 2012 and I began my career with Hokuyo as domestic sales in Japan. And since 2017, I have been working at Hokuyo Amsterdam Branch, where I'm responsible for sales and marketing.
So my name is Leonardo Tan. I've been working in KELO Robotics as software engineer. And today I will do the demo part for the session.
So, hi everyone, thanks for joining. I'm Armin Shahsavari. I'm COO and co-founder of KELO Robotics and a certified functional safety engineer. And I've been working professionally in the field of robotics for 18 years. So let's first start about and talk about the KELO Robotics. KELO Robotics is a company founded in 2020 as a joint venture by two older companies. These two companies brought basically the technologies that they have been developing for more than a decade together and continue to proceed under the name of KELO Robotics. So we have two main branches of product. One is for industrial robots and components for intralogistics. And the second branch is the modular prototyping kit or the Robile product family. So, but you need to know that basically the technology and the philosophy between all these two branches are quite similar. It's both based on the high modularity and our drive system that later we will discuss about that. So let's talk about the AMR, the autonomous mobile robot. First, we take one officially definition of the AMR, which we took from the ANSI norm R1508. I will just read it. AMR is a platform that dynamically plans and adjusts its path within a structured or semi-structured environment to reach its destinations. So if I want to explain it a little bit, we can think we have a robot which is working in a big factory, and it has a task to normally take some stuff or pick some stuff from point A, bring it to point B. And when we set a coordinate in that factory as a destination, so the robot should be able to plan the path to the destination, considering all the dynamic and static obstacles around that. And also with during this drive, if something happened, there would be some dynamic obstacles, should be able to adjust the path. So that's why we have this adjusting. And then when we are talking about the structure or semi-structure environment, it means that we normally don't expect an AMR work out of the box in a new environment. So it means that we need to basically define or predefine some stuff like the map, forbidden areas, and so on and so forth for the AMR. So that's why we are talking about structure or semi-structure. comparing the AMR to the AGVs, so AMR is basically a newer generation of these autonomous systems that we can call them decision makers. That's where they can work in a more dynamic environment. AGVs basically they were the following the predefined rules, like you can think about the magnetic tapes which is attached to the floor that they have to just follow. So where we can use the AMR, basically anywhere that we have repetitive, physically demanding tasks, and with the staffing shortages like warehouses, hospitals, factories, and so on. Please have in mind that when we are talking about the AMR, we are talking about the mobile robot, which is autonomous. What is on top is application specific. It can be an arm, it can be a lifting mechanism, or anything else. So AMR is what it is carrying this mechanism on top. Okay, now we are going to decompose an AMR in three main sections, which is input, logic, output subsystems. When we are talking about the input in a robotic system, specifically in an AMR, we are talking about the awareness of the system. It means the robot should be aware of its environment to be able to interact with. So basically it's sensors. Then we have the logic or intelligence. It means that by collecting this information from the environment, should be able to analyze that and make a right decision. And yet at the end, we have to have a system that we can execute those decisions. So we are talking about the motors, actuators. But above all, we have the standards and safety, because in all these parts, we need to take care of the safety of the human around this system. So that's why there are several norms. These are some examples only here. Depending on the application, we have to take the norm, and also the system should comply with these norms. So let's talk about a little bit about the safety. This is very simplified version of the safety compliance procedure. Normally, depending on the application, we have to first identify the risks and assess them. And then we have to come up with some solutions to reduce or mitigate the risks. And then we have to assess the system and see if it complies with the norm. If not, we have to go to this cycle again and again to make it compliant. So we need. It's good to know that companies like KELO Robotics and Hokuyo can offer you either certified and pre-certified products or certifiable ones, and help you significantly in this process and ease the process for you, basically. So speaking of the decomposition, the first module that we discussed, it was the input module. So the input module is all the information, the essential information that we have to collect from environment to have a autonomous mobile robot. So the first one is the relative motion, also known as odometry data. So the robot needs to know in each iteration of the control in which direction, how much it has been moved. So this calculation is basically the result of reading all the encoder values from the motors. For example, KELO Drive system has a high resolution absolute encoder on the pivot axis, and also on each wheel you would be able to read the encoder value, velocity, and position data. And the second essential data is the distance of the robot, distance between the robot and all the obstacles and all the objects around the robot, to be able to navigate or do the obstacle avoidance. So basically the LiDAR, laser scanner, is the solution that normally is used in the AMR system. So odometry data that we discussed, or the relative motion, it's basically the unit that collect all the position and velocity data from all the motors, and consider, depending on the geometry of the system, will calculate the robot basically delta x, delta y, and delta theta. So this is the relative motion. This is, as I said, the result of the encoder values that we read. But the next thing is about the LiDAR. So I would like to ask our colleagues at Hokuyo to take over and explain the LiDAR part.
Yes. So thank you, Armin. I would like to start our presentation with a brief introduction to the company Hokuyo. So Hokuyo Automatic is a Japanese company that was established over 70 years ago, specifically in April 1946. It is a family-owned business with approximately 250 employees. And Hokuyo, we specialize in photosensors ranging from data transmission devices to LiDARs. And our headquarters is in the city called Osaka, and our factory is also in the same city. And we are operating through our office, globally operating through our offices in the US, China, South Korea, and Amsterdam. And from our Amsterdam branch office, we mainly provide technical support to our customers in Europe, Middle East, and also a part of Africa. Yeah, next slide, please. So what is a LiDAR sensor? The word LiDAR stands for light detection and ranging. And how does our LiDAR sensor work? Our LiDAR sensors emit a laser that scans across a wide 2D field, and they measure the distance to object by calculating the time it takes for the reflected light to return to the sensor. And just like in the picture on the bottom right, which is a top view of LiDAR scanning, our LiDAR scanners measure distances in the 2D scanning field. And the yellow area is the scanning field of the scanner. And typically, the scanning field is 270 degrees. The raw measurement data you get from the scanner enables localization, obstacle avoidance, and navigation in the robotic mobile applications. Next slide, please. So since our very first LiDAR release in 2004 and the first release of our safety laser scanner in 2014, Hokuyo has been recognized as a LiDAR manufacturer. And over the years, we have developed a wide range of scanner models, continuously improved the performance of our products. And to make things simple, we divide our LiDAR scanners into two main product categories. The one is safety scanners, and the other one is non-safety scanners. Yes, and the safety scanners. Oh, sorry. Can you go back to the slide before I wasn't done? So the safety scanners are certified by TÜV, UL, and all our LiDARs, including the non-safety scanners, are CE marked products. And within the lineup of safety scanners, we offer 3 different models. 2 models with standard IO types, and the other one that support EtherCAT safety. And these safety scanners are typically used for AMR applications, for navigation, but also for human safety purposes, which is also a requirement of the previously mentioned safety standard, ISO 3691-4, for industrial truck, autonomous trucks. And for non-safety scanners, we have many different models, and we will show you a table of these models in the next slide. Yes. So this table includes a subset of scanners in our lineup and overall specifications like distance, accuracy, and response time. These are basically all the models that provide raw measurement data. However, some scanners are considered as hybrid models, such as URM40, USD30LC, where it is possible to set obstacle detection zones in the scanner, in addition to raw measurement data output. And there are short-range scanners like USD scanners, ranging from 5 to maximum 30 meters, depending on the model you choose. USD 10LX, for example, is the device that KELO integrated on their robot. It has 10-meter measurement range with angular resolution of 0.25 degrees. And this is the most common option for indoor robot navigation. And there are many models that are designed also for outdoor applications like USD 30LX, URM, UXM, and also UGM series. And these outdoor models have higher rating, IP67, and also a function called multi-echo function, which enables you to filter out dust and rain. And there are also a few 3D laser scanners in our lineup, like YBT series or YLM10LX, which we have very recently released. Yeah. The next slide, please. Yes, so this is our safety laser scanner called UAM05 NPA series, which has been released last year. And this is the other device actually that KELO integrated in their robot. And it is a safety certified device according to relevant standards. And it is certified by TUV and UL, which allows us to reach out to European and US market. Yeah, so the scanner is designed very compact and feature-rich. The compact size make it easier for our users to integrate the scanner into their mobile robot. And rich set of safety function allows our customer to use the scanner basically for any kind of safety application, including AGV or AMR applications. The scanner is a hybrid model. That means you can configure the scanner for hazardous area monitoring and also for mobile robot navigation using its raw measurement data. And it is possible to configure up to 30 meters warning zones, which are non-safety, and 5 meter for safety protection zones. And raw measurement data is available through its Ethernet interface, and you can get maximum 40 meters distance data with angular resolution of 0.125. Okay, yeah, next slide, please. And this is how our software for the safety scanner looks like. It's called the Project Designer. It's a very simple and user-friendly software. Just by following a few simple steps, you can complete the sensor configuration. So you connect the scanner to your PC, go to General Setting, where you can name the device or set the desired IP address, and then go to the function setting. Here you can set how many areas, for example, you want to use, and also which function to activate. And in the area setting, you simply draw detection zones as you wish. And then in the end, you confirm all the settings and write them into the scanner, and the scanner is ready to operate. They're very simple steps. And yeah, from our side, this was a quick introduction to Hokuyo LiDAR, and I would like to pass it over to KELO team.
Yeah. Okay, thank you. So far, we covered the input subsystem of the AMR. So far, we could collect the essential information from the environment that we need to be able to localize ourselves and navigate. But what does it mean exactly, and how it can be done? It's part of the logic system. So logic. For this part, I would take one example that we all are familiar with, which is when we are using the app like Google Map to navigate and reach a destination. So if we review that procedure, basically we define a destination that we want to go. And this type of apps basically start to first localize us within the map. So for that, normally they use the GPS data to be able to localize where are we at this map. Then they plan the route to the destination, considering all the streets, all the obstacles, or all the problems that probably it's occurring in that time, for example. And then when we start to navigate in that path, it's also instruct us like turn left, turn right. And in that context, basically we are part of the loop, and we execute those instructions in the environment. Back to the context of robotics, basically localization is answering the question, where am I? So the robot needs to know where it is within the map that it's working, or within the environment that it is working. Navigation answers the question, how do I get there? So basically do the path planning and how it can reach the destination. Again, I'm highlighting the point, it can be dynamic or static obstacles. And at the end, for the robots, this instruction like turn left, turn right should be executed with a motion system that can be motors or different actuators. So in this example and in this session, and normally also it's common in robotic community, ROS is used as a middleware to be able to write the codes and execute the codes. So, and as we discussed, decision-making is part of the logic, and then also instructing the robot to which direction to move. can be done in the logic part, but we need to have also one part which we said is the output, which is responsible to execute those commands in the environment. If you're talking about the motion of the platform that we need to basically navigate in the system, so let's imagine the logic part is kind of telling us in which angle, with which velocity should we move. Also, how should we rotate around the axis of the robots, which is basically linear velocity and angular velocity on the platform level. Then we have a unit to convert this vector of motion to the command for each motor. It means that each motor on the system should move in with which velocity, in which direction, to be able to execute the command from the higher level of the software that we have. So this calculation is part of, it depends on the kinematic of the system, geometry of the robot, and motion type that we have. So if we want to talk about the motion types, so we can say that we have two main categories of the motion. One is holonomic, the other one non-holonomic. Holonomic is like omnidirectional drive. So it means that the robot can instantly decide and move to any direction. So like this, for example, the robot wants to park in this spot here. So it can just go forward and instantly go sideward to the parking station. But for the non-holonomic, like differential drive, like tank, or even you can think of car, you need bigger space to do the maneuver, to do such parking. You can easily imagine how beneficial it is to have an omnidirectional system, especially in the tight spaces like factories with the narrow corridors and so on. For the omnidirectional drive, two famous examples or two popular solutions. One is mechanon wheel. So of course, the other one is the KELO drive principle and the principle of the work of the KELO drive. The mechanon wheel has basically lots of restrictions, which kind of makes it inappropriate choice for the industrial application. But the KELO drive system, I would say that it's not only the wheel, it's a compact omnidirectional unit of wheel, motor, and drive system. Basically, you need to connect the power and communication. Everything is compact in one system that gives you the omnidirectional characteristic, which is suitable for industrial application. So here I would like to talk a little bit about the principle of the work of the KELO drive system. You can see these two moving wheels here. So each KELO drive system has a fixed plate on top that you can use it to attach it to the robot, so to the fixed platform that you have. And it has two hub wheels that independently you can rotate them and control them independently. And also it can rotate around its axis basically without any mechanical limit, 360-degree continuously. So then, so you have a system with a fixed plate, it can rotate around itself and move to any direction. So here you can see if we attach 4 KELO drive in a platform, you can think that each wheel is able to exert the force to the mounting point. And the sum of all the vectors of these forces would be translated at the end to the linear and angular velocity of the whole system. So basically you can calculate each wheel should exert the force in which direction to be able to have the desired motion that you want to have on the platform level. Behind this, there is a profound calculation, a mathematical calculation. If you are interested, this is a very useful source. It's a PhD thesis that you can read, and there you can find all the mathematical calculation for such drive systems. You can see also on the right side the KELO drive in action, how it rotates around itself and it can move to the direction. The KELO drive system has lots of advantages, including it's compact, it is efficient, it has uniform performance in all directions, unlike the mechanon wheel. You can send or use it in the velocity mode or torque or force mode. It's maintainable. Depending on the type that you use, you can go up to 500 kilogram payload. It can handle the slope of 10%, which is the highest slope that you can normally have in the industrial environment. And as you can see also two of the examples with the two different payloads in this photo here. Then I would like to talk about the KELO Tulip. It's an open source software. It's ROS1 and ROS2 compatible. This part is basically, you can take it and it would be a quick and easy way of integrating different configuration of KELO drive for a robot. It can start with one wheel only, or 2, 3, 4, 5, 6, whatever you want. You can easily configure it, and all this mathematical calculation that I said is integrated or implemented in this part, and you can also read the code. As I said, it's open source. On one side, you can give the v omega command, which is again linear and angular velocity. It does the inverse kinematic calculation based on the robot geometry that you defined, based on the application that you have. So at the end, it calculates all the motor velocity commands, and also it takes care of the EtherCAT master communication. It's a communication protocol to all the wheels that we have. It takes care of the communication with the high frequency. And on the other hand, reads all the encoder values, with the forward kinematic calculate, and with the integrator calculate the odometry data, V omega, and also pose of the robot. So the KELO Tulip here, it takes care of the communication and gives the command, and also gives back to you the odometry data. So now we can get a little bit practical here. So far, whatever we discussed, it was more about the theory, how you can use the KELO drive system for an AMR, and also Hokuyo technology for the sensing. But now we want to get more practical. So for this, we are using the KELO Robile product, which is a highly modular system. You can see it's like we have some bricks and building blocks. Each one has its own functionality. Mechanically, you can assemble them easily together, I would say in half an hour. And cabling is also an easy task to do. And the cable management, you can finish basically the hardware in no time. And you will have an omnidirectional platform, which can carry, this example, 400 kilogram. And then what is on top, it depends on the application, type of sensors, and so on. You can attach anything to that. It's basically, it enables you to shortcut the hardware development and just focus on the software development for any application that you want. So for the mechanical part, there is a detailed video on our YouTube. I don't want to go to the detail here. It's 5 minutes video. You can watch this later. There we will show how you can assemble the bricks together. We have a variety of fasteners and different accessories, and the mechanical parts is all compatible with the standard aluminum profile. It makes it not only easy to assemble, it's also, we make it easy to expand it to other systems. So later you can watch this video for more details. And after assembling the hardware, the mechanical hardware, for example, in any configuration here, we are making 2 times 3, 2 active wheels here, 2 active wheels here, drive, KELO drive is underneath, 1 computer here, and 1 battery system. Then you just need to make a daisy chain of communication, cables connection, and power connection within all, and do the cable management easily also with these cable docks that we have. Then at the end, you would have a complete hardware that you need. Then also, sorry, I forgot, we have also video that shows how exactly you can do that. I just skip over it. We have also another video that shows you how from that hardware you can install and configure the KELO Tulip. And at the end of that, you will have a robot that you can send a V omega command and it moves. So in this example, for example, you can see how with the joystick you can control the robot and move it omnidirectionally. But you can imagine later Leonardo will show you that how the software stack for the navigation actually generates this V omega command instead of joystick in this video. So These are the links. Later, we can also share the links to these 3 videos. Then when you make this configuration, of course, you will have the AMR with the software. But normally, as I said later, that AMR is a system that you want to attach something on top to do something in the environment. So there, the robot provides you with lots of open interfaces, mechanical interfaces. As I said, you can attach different accessories. It's like standard aluminum profile, different structure on top. Also, electrically, you have EtherCAT, Ethernet, Wi-Fi, USB 3, HDMI. Basically, you can expand it and attach different sensor types, RGBD cameras, or whatever you want, depending on your application. So basically, you can expand it to the bigger system. Here is what we have right now here that Leonardo is going to, on the live demo, show how you can deploy the software on it. So I will review what we have. We have 2 active wheels, 4 active wheels, sorry, on each corner here. We have the CPU system, battery system is in the configuration of 2x3 attached together, like the video that you can see. The Tulip, KELO Tulip is installed and configured for the motion. Also, 2 Hokuyo LiDAR is attached. In this example, actually, we are using 2 different types of Hokuyo LiDARs to show that how flexible the robot can be, how different variety of product Hokuyo can provide. But you can decide to use 1 type only. We have 2 sensors to cover the 360-degree coverage here, and also the software deployed here. We have basically software from the ROS, which is available, the Hokuyo software that provides you with the sensor driver, and also KELO software that we have a couple of examples for the navigation. Leonardo is going to take 1 example and modify it for this configuration that we have. So, Leo, you can take over. Yeah.
Yeah, so I can explain a little bit about the software layer. So today we are going to use the ROS Nav2 package. This is an open source package that will provide the ability for the navigation. And in order to get this package working, there are several packages that we will need. The first packages are the driver packages, which is the KELO Tulip, and also the URG Node 2 package from Hokuyo for the LiDAR. And then we are also going to need the robot description package, which will provide us with the model of the components, the bricks, and some sensors. And then finally, we also will use this robot ROS2 navigation package. This will provide us with an example for the navigation to config files and launch files. This is not mandatory, but this will make us easier to implement this because there are some examples already with different robot configurations. So on the next slide. So now we will do the demo. The first step will be to integrate the URG node LiDAR, the Hokuyo LiDAR.
Leonardo, whenever you want to share your screen, I can stop sharing.
Yes, maybe I share. Yeah, can you see my screen? Yeah. Okay. So we are going to set up the URG Node 2 package on our robot. And then on the next step, we will create, on the next step, we will need to create a new model for our new robot configuration. And finally, we are going to create a new example in the robot ROS navigation package to create the proper configuration for our navigation tool. So first, we start with the URG Node 2. So to cut the time, I already have the URG Node 2 package installed. Now what we only need to do is to configure the config files. of the LiDAR, because currently it is still using the default IP address from the package, but this is not the IP address that we are going to use. So I will change it to this IP address because this is the one that I configured with the software. And I will also change the frame ID to scanner. This will be dependent on the model that we will use later. But for now, I will set it to be this value just to make it easy for us. And then for the second scanner, I will change again the IP address and change the node. Okay, so now we can compile and then we can launch. Okay, so it seems like it is running. And we can see that the topic is being published. Now we can try to visualize it with RFIS. So in RFIS, currently we cannot use this fixed frame because we haven't set up the model. So for now, we need to use directly the scanner link that we already set before. And then if you can see, when I set it up, you can see now the laser points from the first scanner. And if we change it to the scanner to link, we can see the laser points of the second LiDAR. So now, as you can see, this is my hand. You can see that it is detecting the scanner. So now we have the hardware running. For the KELO Tulip, we already configured it. And the configuration, as Armin said, you can watch it in our YouTube, or also you can see in our GitHub. There are much more detailed examples and also explanations on how to configure it. Yeah, so for now we skip it and we go to the next step, which is to create a new model for our robot. In general, because the robot itself is very modular, we also create this package so that all the bricks, they work as a...
Come on, come rein.
Sorry. So we set up the model to be configurable, basically. Like, so for example, this is one example of a 4-wheel configuration with 2 UAM 05 LPA Hokuyo LiDAR. And you can see this is like the building blocks that we use. For example, this is the active wheel brick block. So we have 4 of them. And then we can simply add the CPU brick also and the master battery brick. And you only need to set up the origin, the coordinates of the block and also the orientation. Then you can already have the model being loaded correctly. And for the sensor, for example, we added already the Hokuyo, 2 Hokuyo sensors, this Hokuyo UAM 05 LPA. But for this demo, we are not going to use 2 of them. We are only going to use 1 of this, and we are going to use a different Hokuyo sensor, which is this Hokuyo UST 10LX. So the easiest way for us to create a new one is to simply copy this file, and then we can change this block. So I will show the example. So we copy this, and let's say we name it UAM USD config sacral. Now we need to edit the file. So first we need to include the new sensor to the sacral file. And luckily we already have it also in our robot description package. So what we need to do is to check the directory. And then we have this file. We can use this. And it is in the same directory as the other sensor. So we can just copy this, and then we replace it to include our second sensor. Okay, so now we already included the information about the block, and now we need to replace this block down there. And then in order to change it, we can simply see the details about the file, and it tells us that this is the name of the block. We can copy, and then we can replace this. Yeah. In general, if you are using different scanner, you might need to change also the origin of the sensor. But in this case, because we are using a special holder, it is using exactly the same position, so you don't need to change it for now. Yeah, so now we have the model finished. The only thing which is missing is just to create a new example for this mobile cross navigation. So here in the GitHub also you can find later the more detailed explanation. But for example, I can explain to you just the overview of the package. Wait, sorry. I think to move to the master branch. Yeah, so this is the example. And for example, this robot.launch.py, this is going to be our main launch file. This is going to call all the other launch files that we will need. So for example, this bringup.launch, this is going to call all the drivers that we will need, all the hardware interfaces that we will need. We will put it here. And the second part, which is also important, is this navigation launch part, which is going to call all the navigation 2 packages. Maybe I can show you shortly. Like in this case, in this navigation.launch, we can see that it is calling the behavior tree, the planner, the controller, and also the behavior servers. Everything is already configured. You can, if you want to make some changes, you can just simply change it in the config folder. You can change for each server the configuration that you want. But for our case, because this robot is very similar to our test demo software platform, then we don't need to do much change here. So the only change that we will need to do is in the hardware side, basically. And sorry, and we can see it in this bring up package launch file. It will start the KELO Tulip. It will start the joypad also, and it will also start the LiDAR launch. And this LiDAR launch, if we see closely, it will include the Hokuyo driver launch file, and also we will add one merger node, because in some packages, like the localization package, it only receives one scan. So we need to combine the two scans into one scan to make it work properly. So for the demo, what we are going to do is we are going to copy this file, the four-wheel demo, and then let's say we name it four-wheel AMST, let's say. And then the only thing that we need to do is to change the platform name to suit our folder name, because this is going to be used to set up all the directories in here. So we need to fix this. We need to get the correct one. And then also the model name. So this should be, this is the name of the file that we just created today. So this is correct already. So all the directories are set up correctly. And in general, also, we might need to change, oh, sorry. We might need to change also this LiDAR.launch if we use different type of sensor. But since we are using the Hokuyo sensors now, it is not needed, because Hokuyo driver will handle all the types of these Hokuyo sensors, and we don't need to take care so much. So we just need to specify that we have two sensors, which is the same as in the example, this four-wheel double UAM. We are going to use exactly the same launch file, and this should already work. The last thing that we need to do is simply, because we created new folder in the example file, we need to configure the CMake list to include the folder that we just created. So everything will be compiled and installed. So this is the, okay. So now everything should be configured, and we can compile, and then we can simply, maybe I start first the harvest, and then we can launch. Okay, so everything seems to be running. We have everything, and then we just need to give the correct pose, let's say. Oops, wait. And maybe it is somewhere here, for example. Yeah, and then we just, yeah, when it is already localized, we can just give a pose, a goal pose, and then it will drive, basically. So this is finished. But for the demo, let's say, because it is really tight space here, we already create a video which Armin will show.
I hope you can see my screen now. So maybe I just explain, as Leo mentioned, those steps are done. If Leo, you can mute the microphone, that would be great. Thank you. So, and then we did the same test with the navigation and the corridor just outside the office here. And here you can see the video of that in parallel for the simulation and the real robot. So Leo just defined the destination here, and robot is autonomously navigating at the path planning and navigating toward the destination. I guess we can start the Q&A session.
Okay.
So I guess you collected the questions, you can ask them depending on the question, one of us should.
Yes, sure. Thank you, the speakers first, and thank you, the people who have listened to our speakers. Now I have collected some questions. The first one is that I think that Armin can answer to that. Is V, so in the V omega command, is it the forward velocity or is it a vector with two components, Vx and Vy?
Yeah, actually, it's vector. We are talking about the on the platform level 2, 3 degree of freedom. It means that it's a vector to any direction, the linear velocity. It can be in any direction, and also if we are talking about the vector, the length of the vector is talking about how fast or slow it can be. And also angular velocity is also the rotation of the platform around its axis that you define in the geometry of the robot. Yeah.
Okay, great. So the next question is that, can you provide a deeper comparison between the mechanism wheel and the KELO drive system?
Unmute. I will also take over. Okay, the mechanism wheel, this is the photo that you see here. You know, it has, you can imagine this wheel will have, for example, there are a couple of points that we can compare. This wheel has a different characteristic when you are talking about the motion moving in this direction or the side direction. So this means it makes it more sensitive to the unevenness of the ground. But for example, for the KELO drive, since this is rotating to the direction of the motion, then you will have the quite similar behavior in all the direction that you move. So basically it's unevenness and more sensitive to the environment and the flooring, and dealing with the also gaps on the floor, for example, this is one thing, and the sudden changes on the floor that you have. And also the complexity of the mechanism, it makes it more prone to have mechanical failure, and some stuff gets stuck between these wheels, for example. So as I also mentioned in this slide, KELO drive is basically fill this gap between the need of omnidirectional solution to the industrial application. It means that it provides you a omnidirectional solution with all the requirement that you need for an industrial application. I hope I could answer the question.
The next question is that, is the complexity of an omnidirectional drive system worth the efforts compared to a simple differential drive system?
Okay, it's a very good question. I must say it's very application specific, but I can tell you, you know, when we have the robot should work in the narrow space, tight corridors, close proximity to the human. You need some maneuvers that with the differential drives, it's either impossible or very hard to do, you know. So of course, on the hardware level, when you are developing the system, you're adding a little bit of more complexity in your design. I understand there we are talking about two motors, two wheels, but here we are talking about more actuators. But all the degree of freedom that you get and all the maneuverability that you get, it will ease the way in your deployment and integration. Couple of maybe complexities that you will have in the software development, how to do the kinematic calculation and so on. The good thing is that, for example, with the open source software like KELO Tulip and the software that you have, basically all this part complexity is already addressed and solved. You can just take it, and since it's open source, you can also customize it if you can improve it if you need. At the end of the day, I would say that there are many applications that the omnidirectional is the solution, not an option, because you need the omnidirectionality for that. But for the other ones, since with the newer technologies like KELO Drive system, which makes it easier and modular to connect to just power and communication, and you have the open source software on top, you basically shortcut all the complexity. You can benefit from just the mechanical advantages that you will have with the omnidirectional platform.
Okay, great. So I think now we have a customer question. Our KELO wheels shipped with Ubuntu 20.04. This demo is with ROS 2 with Humble, which requires Ubuntu 22.04. Should I use Docker inside Ubuntu 20.04?
Okay, so I will answer this question. In general, you have a few options to do this. You can always, of course, reinstall your PC with the Ubuntu 22 and run the ROS Humble there. This is one option. The second option is actually if you want to run the ROS2 Foxy with for the ROS2 navigation. This is also possible, but from what I remember, there could be some features or configuration files which is a little bit different compared to the Humble version. So this you might need to check a little bit. As far as for the Docker, it is also possible to do that. But from what I remember, I needed to set some special permission for the Ethercat connection. So you need something special in the settings, basically.
Yeah, maybe as Leo mentioned, the Robile, we always claim it's an open platform. So that's why the CPU comes with a pre-installed software, but you can always install anything that you want, including the newer Ubuntu or newer ROS, and using again the code on our GitHub to deploy those codes on the new system.
Okay, great. So the next question is it possible to custom design an add-on for Robile that does not currently exist in your product lineup?
Oh, yes, definitely. You can basically, the accessories that are available is for popular components and commonly used components in the robotic community, including like the Hokuyo sensor, for example. We provide them already, but since it's a standard aluminum profile, mechanically, it's a standard aluminum profile, and also the step files are available, we can share it with you. You can design any add-on or component that you want, or even you can 3D print them, for example, to attach. And electrical also, we have basically all the interfaces that you need, like Ethernet, EtherCAT, to be able to expand it. So it's your decision to use the available accessories or you make your own. Even we have the empty brick. You can even buy an empty brick and design your electronics and component and put it in a brick, and it's mechanical also incompatible with the Robile ecosystem.
Okay, great. And the last question until now, what should we do if we have a project that needs a specific config, but we are not sure which Robile components or sensors are the best fits?
Yeah, that's a good. I can answer the question from KELO side also. The Hokuyo side also can answer for the sensor. Definitely, you can always contact us, and we normally set a meeting to discuss your application to understand what is exactly, and we try to introduce you with the proper components that you would be able to use it. For your application, do you need 4 wheels? Do you need 2 wheels? Do you need which type of CPU do you need? So, and also accessories. And speaking of sensor, I guess probably Hokuyo has the same service, but please, Maris, you can go ahead.
Yes, at Hokuyo side, you are always welcome to contact us. We do have a variety of products in the safety and in the non-safety, and we'll be very happy to support you to choose the right model and also to support you in integrating it down the road.
Okay, great. So I think that we are finished with the questions. So special thanks again to Dr. Christou and Mr. Yamazui from Hokuyo. And here are the contact information of the speakers from Hokuyo and from KELO. Thank you so much.
Thank you all.
Thank
Bye-bye.
Bye.
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 Bye bye.